In this video, we're going to look at how we can solve problems involving objects in motion using vectors. To start things off, we're going to consider a plane flying on a northwest heading between cities A and B. The intended path of the plane is shown here. Now, ideally, the plane would be able to take off from the airport in city A and fly directly to city B on its intended path. However, there's a wind blowing in from the west, so an easterly blowing wind is going to knock the plane off course. If I draw the intended path of the plane, so the route it's actually flying, tip to tail with the wind path, then this red resultant vector represents the actual course of the plane. So what's happening here is as the plane tries to fly directly from A to B, the wind is progressively nudging it further and further off course, pushing it onto that red course, which puts it a little bit further east from where City B actually is. You've likely experienced this phenomenon if you ever have gone swimming in an area where there's a strong current. If you try to move from one side of a stream to another, you'll notice that despite your best efforts to go directly across the stream, the current is going to push you downstream gradually as you move across. The only way for you to end up where you intended to go in this situation is for you to actually not walk straight across the stream, but to walk into the current. As you walk into the current, the force of the current pushing you along is actually going to ultimately get you right where you want it to be. The same is true for an airplane flying between two cities. If they want the speed of the wind to push them on course, they actually have to chart a course that goes further past the city or goes into the wind further so that they end up in the right spot. So by going along the vector I've marked here in purple, the plane will be moving into the wind, and the speed of the wind is going to progressively nudge it back onto the intended path, and so it will still be then flying from city A to city B. So now that we've seen how that works conceptually, let's actually deal with some concrete values here. So a plane is flying with a velocity given by these unit vectors, so negative 360i plus 400j kilometers per hour. So that's the velocity of the plane. It's indicating to me direction and how fast it's going. A constant wind is blowing from the west at 60 kilometers per hour. So that is also giving me the magnitude or how fast it's going and the direction. But here, it's worth noting the direction is given in words. So if something is blowing from the west, that means it's heading to the east. So I have a sense of the direction of that vector. The first thing I'm going to want to do is determine the resultant velocity of the plane. Basically looking at where is it going to end up, or how fast is it going overall as a result of the combined velocity from the plane itself and from the wind speed. So here it's important to remember that the speed of the plane plus the speed of the wind equals its overall speed for the course that it's going to be on. So I can think about it from a geometric standpoint, and I've drawn a diagram there. I can also think about it from an algebraic standpoint. I've constructed a vector equation where p plus w is equal to c. So to find the resultant velocity c, I really just have to add together these two vectors. And I have their unit vector components that they're made up of, so this is actually a very simple operation to do. The vector of the plane is negative 360i plus 400j, and then the vector for the wind, remember it's coming from the west, so it's heading to the east. That means it's heading to the right. So I would represent it using a unit vector I, and because its speed is 60, that means it's actually 60i is how I would represent that vector. So the resultant velocity of the plane is given by negative 300i plus 400j. So that tells me that overall the plane is heading to the northwest, just like the example we looked at before this. Now what I might actually want after that is to know specifically what speed is the plane going. So this is the velocity. It's telling me how quickly it's going, but it's also packaged in there with the direction. If I'm not worried about the direction, if I'm just worried about the speed of the plane, what I actually need to find is the magnitude of that vector. So when I calculate the magnitude of the vector c, I end up with an answer of 500 kilometers per hour. So that's roughly the speed that the plane is traveling overall when you combine its speed, the speed that's powered by the plane, and the speed of the wind all coming together. Now, another interesting thing that might be required in this situation, because now we're dealing with a real world object moving and we want to know how to chart its course, we might actually be curious to discover the bearing that the plane is going on. So here I've drawn the components of the plane's overall velocity. It's going negative 300i, 400j, so that means it's going to the left 300 and up 400. I could actually connect these two vectors to make a right-angled triangle. And so to find the bearing, if this is north, my bearing angle is measured from north all the way around until I end up on the course it's actually flying on. So this side length here is vector c. So I want to find that overall angle. Now, I know because I passed through the first, second, and third quadrants that the bearing is bigger than 270 degrees. What I really need is this angle of theta in here to kind of complete the picture. Because this is a right angle triangle, I can simply use SOHCAHTOA, my primary trig ratios, to solve for that angle. I have the side opposite to the angle and the side adjacent to the angle, so I can just use tan here and say that tan theta is equal to 400 over 300. When I solve for the angle in degrees, I get that theta is equal to 53.1 degrees. Now, if I remember that this is only part of my bearing, I still have that additional 270 degrees that I've already gone through but didn't have to consider for this triangle. My overall bearing, which I'm just going to call beta, would be equal to 323.1 degrees. So this is the kind of general problem that you'll see involving objects in motion where multiple vectors are at play. The types of questions you typically see will involve planes flying through the air and a wind speed affecting them, or an object moving through the water and the current of the water affecting them. These are the most common types of problems that can be addressed in this way. But of course, they're not the only problems involving motion that we can look at with vectors. We can actually use our vector equations of a line to come up with a really useful vector equation that models the movement of any object based on the parameter of time. So the motion of objects moving with a constant velocity can be given by that same vector equation, r is equal to a plus tb. Now the parameters have slightly different meanings here, just to connect them very clearly with the physical situation that they're involved in. So first of all, the vector r represents the position vector for the object at the time t. The vector a is the initial position vector that represents where the object was, and the vector b represents the constant velocity of the object in motion. And of course, because t represents time, we know that t has to always be greater than or equal to 0. So let's consider a real-life example that actually extends into 3 dimensions. We have a model airplane, and it is currently at the point 356. So that means it's a certain position relative to the ground, but it's also in the air right now. 6 meters in the air, according to that z coordinate. And it's moving with a constant velocity that's given by that vector there. V is equal to 2i minus j plus 3k. And that's in meters per second. So if I wanted to come up with a general equation that represents the position of this plane, I would use that equation we had just written out, r is equal to a plus tb, and I'm going to pop those vectors into their appropriate positions to get a good vector equation here. And so I get the vector equation r is equal to 356 plus t times 2 negative 1, 3. Now that I have that vector equation, I can answer all sorts of questions about the motion of this plane. For example, I could calculate where its position is after it has been in the air or been in motion for 4 seconds. To evaluate that answer, I'm just going to plug 4 in for the value of t and figure out the overall position vector, which I get as 11, 1, and 18. So it's moved around a little bit in terms of my x and y values. It's also gained a fair bit of altitude. It's 3 times as high into the air as it was to start with. Evaluating where an object is at a certain time is a fairly straightforward process. The really interesting questions come up when we try to figure out when the plane is closest to a certain point or when its position relative to a certain reference. So I've posed here the question, when is the plane due east of the point 0, 0, 0? To solve this problem is actually going to take a little bit of thought. If the plane is due east of something, that means that it can have an x component, because that indicates its movement west or east. But it shouldn't have any y component, because that would indicate motion north or south. And if it's supposed to be directly east of this point, it means it has to have the same north or south component that goes with it. And so what that means is the y component of the position vector that I solve for here has to be equal to 0. So I'm going to take that information, the only information I really know, and plug it into my equation for the motion of this airplane. And if you look now, I can't actually solve for everything in each component. If I look at my parametric equations for x, I have x is equal to 3 plus 2t. And for z, I have z is equal to 6 plus 3t. So I have three variables in those two equations. I actually can't do anything to solve for them directly right now. But if I look at my y component, by knowing that the y component has to be 0, I now have an equation that only has t in it. And so I find out that this happens when t is equal to 5. So after 5 seconds of flying from its initial position on the vector it was going on, this plane will be due east of the point 0, 0, 0. I can even figure out the coordinates of where it will be now by plugging that t value into the other equations. So when I plug t into x, I get the value 13, and when I plug t into z, I get the value 21. And so that means its overall position vector is 13, 0, 21. So that's telling me that it is 13 meters east, it is 0 meters north or south, and its altitude is 21 meters. This is only a sample of the kinds of problems involving motion. There's a lot of different variety here. Sometimes it involves tangible real-world objects like airplanes or boats and things like that. Other times it's a little bit more abstract, talking about the motion of a particle moving along a line or moving on a spring. And so you'll see a lot of variety there, but the important thing to remember is that an object in motion is no different than any other object in motion. You'll be given information about it and tasked with solving a problem, and the actual nature of the object is irrelevant to that solution. All you have to remember is that things have a starting position and things have a velocity that affects them, and that's how you can solve all sorts of problems using that information.